Hello everyone, I'm in Gowri Shonali, Inspired Fellow as SRF, working with Dr. M. Sridharan. My thesis presentation title is Surface Modified Zinc Oxide Nanostructures for Ammonia Reduction. Moving to the current status and the motivation of ammonia. Ammonia is a colorless gas with a sharp suffocating odor. It is one of the most common chemicals manufactured and applied diverse areas around the world. Recently, 80% of ammonia has been utilized for producing nitrogen-based fertilizers. Rest of 20% of ammonia used for manufacturing of leather, rubber, food, beverage, mining, petroleum, etc. Additionally, ammonia is a great source of hydrogen. It is often utilized for the automobiles and diesel engines and the majority of ammonia emissions from agriculture, industry, livestock farming. These emissions can create side effects to human disease such as headaches, nausea, loss of appetite, skin damage, eye damage, and neurological effects. And for the animal disease, it is decreased their growth, productivity, fertility, and decreased egg production. And for the common disease or irritation of eyes, nose, and throat, respiratory problems, and lung damage will be occurred. According to the OSHA limit, the acceptable exposure range is 25 ppm for 8 hours and 35 ppm for 10 minutes. If the consuming concentrations are critically high, the prolonged exposure becomes more intense and it can lead to death. According to the global gas sensor market, the compound annual growth rate is 8.3%, increasing the demand of gas sensors. The global gas sensor market is expected to reach USD 4,114.5 by 2027. Therefore, to develop ammonia sensors with the highly selective, accurate detection, long-term reliable, detect low ppm level, room temperature operation is essential to protect environmental safety, human health, and industrial safety. Among the sensors, chemistry sensors has been widely used for the reduction of toxic gas molecules. So sensing element we have chosen zinc oxide. Why zinc oxide? It is an n-type material, the majority carries of electrons. It has a wide band gap of 3.33 electron volt. And these zinc oxide has certain kind of limitations such as higher operating temperature, poor selectivity, low stability, higher limit of reduction, and a larger response in required times. These limitations has been enhanced by using noble metal decoration, heterojunction formation, UV activation, doping, and addition of 2D materials. So, in this work, we are focusing on surface modification of zinc oxide using graphene oxide, reduced graphene oxide, graphite carbon nitrate, mexines, chalcogens. And these surface modification increases surface area. It provides more active sites for gas molecular interactions, and also it helps charge transport, electrical and chemical stability, which enhances sensitivity, adsorption, and reaction kinetics. The experimental methods, zinc oxide has been deposited by using a DC reactive magnetron sputtering, and these sputtered zinc oxide thin films were further surface modified using drop casting technique, and these surface modified sample utilized for the gas sensing measurement using Keithley Harris electrometer 6517B at room temperature. Moving to the comparison of surface modified zinc oxide nanostructures, the pristine zinc oxide exhibit nanograin morphology with a shorter response in required times of 63 and 34 in order of seconds for 10 ppm of ammonia. And the surface modification of pristine zinc oxide using graphene oxide, reduced graphene oxide, graphite carbon nitrate, mexines, tellurium, and selenium. And these efficient images shows the distinct morphological changes after each modification, while sensing graph demonstrate the improved response in required times. Among these samples, the organodecorated zinc oxide shows shorter response in required times for 39 seconds and 42 seconds for 10 ppm of ammonia. The table summarizes the sensing performance of all developed zinc oxide sensors. Among them, decorated zinc oxide sensors showed the highest response and the fastest sensing characteristics. And based on the results, the portable rechargeable ammonia sensing device was successfully developed with the rechargeable system, TFT touch display, LED indicator, buzzer alarm, low power design, and it demonstrating the practical applicability of the developed sensing technology. The findings of my research work have been published in peer-reviewed international journals with a cumulative impact of 47.1. I would like to thank my supervisor, Dr. M. Sridharan, for his continuous support and guidance. I gratefully acknowledge the Department of Science and Technology, Government of India, for the financial support through DST Inspire Fellowship. And also, I would like to thank SASTRA Deemed University for the infrastructure facilities. Thank you.